Welcome to our today's lecture video. The topic at hand are techniques in solving limits. In previous lecture, we celebrated the properties that allows us to determine or obtain the limit of a function using direct substitution. However, in this case of rational function, this approach fails when the denominator becomes zero upon direct substitution. There are two possibilities for this. First, the numerator yields a non-zero value, say a over 0, in which case the limit does not exist because it exhibits an unbounded behavior. Either the function tends to positive infinity or negative infinity, depending on the sign of a. But we will talk more about this in a separate video. The other possibility is when the numerator yields 0 as well. In this case, the limit may or may not exist. We don't know yet. That's why this phenomenon is called an indeterminate form. The challenge now is how to determine if it exists or not. If it does, then what is the limit? The lecture session for today is solely intended to answer that question. In this case, we will employ three techniques in order to locate that limit. Let's go. Strictly speaking, the function g of x and f of x defined as x minus c times g of x all over x minus c are not the same. Almost, but not quite. Their difference occurs at x equals c. Precisely, f of x is not defined at c. Although it is tempting to cancel the common factors in the numerator and in the denominator, it is generally not allowed. However, when it comes to limit of functions, the following theorem has something different to say. By the way, this theorem is also applicable for a function that is redefined at C. But let us focus on the case where it is not defined at C at all. So let f of x equals g of x for all x not equal to c in an interval containing the real number c. If the limit of g of x as x approaches c exists, then the limit of f of x at c also exists and they are equal. So how exactly is this property useful? Well, it says that under limit, almost equal functions such as f of x and g of x, those that differ only at one point, will yield the same result. In short, under limit operation, cancellation of common factors is allowed. For an illustration, let us consider the function f of x defined as x squared plus x all over x and take its limit at x equals 0. Obviously, direct substitution will not work because it will result to 0 over 0. What we can do at least is rewrite the expression into that one, we factor the x out. Using the above property, we can cancel the common factor. Then once again, direct substitution becomes possible.
Wow.
Oh, great. Let us look at some other example. Examples. Solve the limit of the following functions at c. As you would notice, the given rational functions are not defined at the given c value. This immediately tells us that direct substitution cannot be performed. Now, let us try the technique at hand, the cancellation technique, meaning we will try to extract common factors in the numerator and the denominator that could be causing the indeterminate form. In some cases, we need to perform algebraic manipulation first before we can summon the common factor. For number one, we first factor the expression, then cancel out the common factor. Now we can try if direct substitution works. And it does. So we simply simplify the result to 2/3. For the following limits, we simply perform the routinary process of rewriting or factoring, then canceling, then applying direct substitution if possible, and of course the finishing touches at the end. All right, as simple as that. Another type of rational function that yields 0 over 0 when evaluated at x equals c are those that involve radicals. Either one of or any one of these four forms of rational functions that involve radicals. In these cases, cancellation technique is not readily possible because factors that are supposed to be cancelled out are concealed within the radicals. Hence, we first need to expose the said factors in order for us to get rid of them. The process that I just described is called rationalizing technique. If we have a function that contains a radical expression of this form, any one of these, then we want to multiply it by its conjugate, because in so doing, we'll get a product that is free of radicals, like this one. With this new form, we expect to see or extract a factor in the denominator, or the numerator. When that happens, cancellation is now possible. Only then can direct substitution be performed. So you will see what I mean in the following examples. Example 1, solve for the limit of square root of x plus 10 minus 4 all over x minus 6 as x approaches 6. Solution: when direct substitution is performed, we get 0 over 0. As mentioned a while ago, it does not mean the limit does not exist. It just requires us to employ some technique in solving the problem. Since radical expression is present in the problem, let us resort to rationalizing technique. In the given example, the radical expression appears in the numerator. So the first step is to identify the conjugate of the radical expression, the conjugate of square root of x plus 10 minus 4. Once identified, multiply it to both the numerator and the denominator. So here's the product. When simplified, it exposes the common factors, the x minus 6 factors in the numerator and in the denominator. All right. So the simplified form of this numerator reveals the common factors. So what happens next is cancellation. Now, after we cancel out, we try the direct substitution and see if it works. When I say it works, I mean that we no longer get 0 in the denominator. So, and indeed, we get 8 in the denominator. So our final answer is 1 over 8. Number 2, solve limit of x over square root of 2 minus x minus square root of 2 as x approaches 0. Again, you can check that direct substitution fails here as this gives us 0 over 0. So we need to do something. In this problem, the radical appears in the denominator. Its conjugate is, of course, the plus sign. So we multiply both the numerator and denominator by that conjugate. So after multiplying by the conjugate and simplifying, the common factors are now exposed, and so we kick them out. So this is now the resulting function when the common factors are eliminated, and I bet you know what is coming next. All right, as simple as that.
Whoa!
For number 3, calculate limit of 3 minus the square root of x over x minus 9 as x approaches 9, and after we check for the possibilities of indeterminate form, it is confirmed that it will give us 0 over 0 upon direct substitution. So we do something, and of course what we'll do is to use the rationalizing technique that we did in number 1 and number 2. So we'll do just that. Another technique that we will discuss is called the special limits. This involves a limit of trigonometric expressions that are critical in its role in the development of calculus. And so, taking their limits at a given point is of utmost importance. To solve limits such as this, we need to help the property called Squeeze Theorem. The theorem states that if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x in the open interval containing c, except possibly at c itself, and if the limit of these functions h and g that sandwiches f of x are both equal to a real number L as x approaches c, then the limit of f of x itself as x approaches c should also be equal to L. The squeeze theorem basically tells us that we need not directly find the limit of f of x from the function itself. We can make use of the other two functions that are related to f of x in a way that is stated in this theorem, meaning two functions h and g are sandwiching the f of x, the function that we are interested in. Um, when these conditions are met, f of x is kind of squeezed in between these two functions. All right. So the proof of this theorem can be found in Bartel and Schubert. Do check them out if you are interested to know the nitty-gritty of this fascinating result. So with that property, the squeeze theorem, we are now ready to solve the limit of sine x over x as x approaches 0. The crucial part of the squeeze theorem is to find two functions that sandwich the f of x. The good news, though, is that there are many such functions. In this case, we will make use of the concept of trigonometry. the areas of triangle and a sector. More specifically, we want to compare the areas of the small triangle, the sector, and the bigger triangle. Of course, we know immediately that this relationship exists, that the area of the smaller triangle is less than or equal to the area of the sector is less than or equal to the area of the bigger triangle. What we don't know yet are the actual measures of these areas. So to find out, assume first that the measure of this angle, this one, is theta. Since this is a unit circle, we also know that this segment, that one, is of length equal to 1. And these points have coordinates 1, comma 0, that one, by trigonometry. This one is sine theta or cosine theta, comma sine theta. So given these coordinates, we can now identify the height of the triangles, the height of this one and that one. So if those are informations are available, we can now solve for the areas of these triangles. The smaller one has height of sine theta, and using triangle similarity, we can see that the height of the bigger triangle is tangent theta. So we're all set. Let's find the actual measures of the areas. Firstly, the smaller triangle having the height of sine theta and base length of 1 must have an area of sine theta over 2, right? Base times height divided by 2. So that's the area of the smaller triangle. On the other hand, the area of the sector, being a portion of a circle whose radius is 1 unit, must have theta over 2 pi times the area of the whole circle, right? The, the portion of that is theta over 2 pi of the whole area, which can be simplified into theta over 2. Finally, the area of the bigger triangle having the height of tangent theta and base length equal to 1, the area is tangent theta over 2. This relationship can be rewritten as that one. We just reverse the ordering and the direction of the inequality. So tangent goes here, theta over 2 goes here, sine theta over 2 goes here, and we reverse this uh, inequality direction. Multiplying each expression by 2 over sine theta, we will get, here we get 1 over cosine theta, here we get theta over sine theta as 2 is cancelled out, and here we get 1, right? So what do we do next? We take the reciprocal of each of the expressions, because what we need really is sine theta over theta, this form, something like this. But sine theta is down here, theta is up there, so we need to take the reciprocal. But in so doing, because the involved expression do not change their signs as long as theta is in the open interval from negative pi over 2 to pi over 2, the act of reciprocating must reverse the direction of the inequality. So it reverses. We take the reciprocal, we take the reciprocal of this and as well as this, and we reverse the direction of the inequality. Again, that is possible in the interval from negative pi over 2 to positive pi over 2. By the way, smaller interval will also do as long as it contains 0. And the sign upon uh, the sign of these expressions will not change, no, on that interval. So any smaller interval will also do. And now, this is where the magic begins. As you can see, sine theta over 2 is now sandwiched by cosine theta and 1. The, the cosine theta function and the constant function 1. When their limits are evaluated at 0, they will yield what? They yield the same result, both equal to 1. So, that is the conditions that we are needing, that this function that we're after with are sandwiched by two functions whose limits are the same. And can you see what is coming next? Yes, the squeeze theorem. Sine theta over theta being sandwiched by two functions whose limits are both equal to 1 at x equals 0 must also have limit equal to 1. Therefore, here is our special limit. Number 1, the limit of sine x over x as x approaches 0 equals 1. The proof of this result was shown a while ago. Number 2, the limit of 1 minus cosine x over x as x approaches 0 equals 0. And why is that? Well, that is what we will show today. Oh, great. So what happens is we did some algebraic maneuver to elicit the sine x over x expression from this. So that involves multiplying by 1, this one, and then, some manipulations, algebraic and trigonometric identities are used here. We separate, and then by that um, theorem property, this is equal to 1. And when we perform direct substitution here, this is what we get, 0. And so the final answer is 0. So that this property number 2 is equal to 0. We will need these two special limits when we discuss the derivative of trigonometric functions. So please remember this. Examples. Solve the following using special limits. So um, the goal here is to find a way to elicit those special limits out of this. So the first instinct would be for number 1 is to rewrite tangent into sine over cosine, because the special limits, our motivation involves sine and cosine. Then we continue rewriting the expression as So we separate sine x over x and what multiplied to 1 over cosine. Then we can use the multiplication rule to separate the limits because we know that each of these individual limits exist. So multiplication rule is allowed. You can separate them. Now it's time to use the special limits. Great. So the answer is equal to that the limit of tangent x over x as x approaches 0 is equal to 1. Number 2, limit of sine 2x over x as x approaches 0. So the thing about this problem is that the angle and the denominator are not the same. But the special limits requires that these three entities should be the same. Sine of something over something as that something goes to nothing. Yeah, that's the only way we can use that. But as you can see here, the angle and the denominator are different. So again, what does your mathematical instinct tell you? Yes, we can rewrite the sine 2x using a double angle identity. So sine 2x becomes 2 sine x cosine x, and then we separate 2 and cosine here so that we can extract sine x over x. Then again, we use the multiplication rule. Can separate the two, and yeah, you know what is coming next. Direct substitution and the use of special limit as this is now available. This alternative solution is a clever one as it features a way of changing variable under limit operation. This is the first time that we will do this. So first we have to rewrite the rational expression so that the denominator will match the angle of the sine function because as you can see they are different. This can be done by multiplying both the numerator and the denominator by 2. So we multiply both the numerator and denominator by 2 so that the same problem retains. Then um, under limit we can set aside the constant, this 2, and this is what is remained. Now the angle and the denominator are the same. We do that since we intend to make use of this awesome property of the special limit. Again, you see here that these three entities are the same. Before we can use them. So in the problem at hand, the angle and the denominator are already similar, except that one. This is 2x, 2x, but this one is x. This special limit theorem requires that all of these three are the same. So our next move is to attend to that, and that can be done by changing the variable. Now the change of variable is underway. Let y equals 2x. Notice that as x approaches 0, 2x also approaches 0, right? Hence, y being equal to 2x must also approach 0. Now it's time to replace 2x by y in the original limit problem. So 2x becomes y here, and that x approaching 0 is also equivalent to saying that y is approaching 0. Y again is equal to 2x. So that's how we change the variables under limit operation. It now becomes 2 times the limit of sine y over y as y approaches 0. So once again, our good friend says that he is up for grab. We get the 2 times 1, which is also equal to 2.
Wow.
Additional examples use Squeeze Theorem to find the limit of f of x at c. F of x and g of x, by the way. So in number 1, we have a function f of x of which we need to find the limit at 0. What is nice about this problem is, although we do not know what is f of x really, the two sandwiching functions are provided for us. We have 1 minus x squared and 1 plus x squared. On the other hand, in number 2, we have the function g of x equals x sine 1 over x. So the g of x is given. But the sandwiching functions are not given, unlike this one. So we have a problem,
Uh-oh.
but we are ready for that. We will be able to solve that. So let's go. Let us solve first number 1. At c equals 0, find the limit of f of x that is greater than or equal to 1 minus x squared but less than or equal to 1 plus x squared. Since the sandwiching function are already given, we only need to know what their limits are at 0. If they are equal, that is great. Let us see. The limit of the functions at the left is equal to 1, while the limit of the function above is equal to 1 as well. So that is good news. They turned out to be the same, and hence we conclude that using the squeeze theorem that the limit of that function being sandwiched is equal to is actually forced to be equal to 1. Yes, just like that. How about the next one? At c equals 0, find the limit of g of x defined as x times sine 1 over x. Solution. Our first task is to find the sandwiching functions. We can start with the previous limit that we discussed before. It says that the limit of sine 1 over x as x approaches 0 is non-existent. So maybe we can start with that. And that happens because it oscillates. That means the function simply goes back and forth between two values. The question now is, if x is multiplied to sine 1 over x, will it make a difference? What I mean is, will the limit exist now? Because there is x here. Alright, on to the first task. Find the sandwiching function. Firstly, we know that the trigonometric function sine is a bounded function. No matter what the angle is, its value is always in between -1 and +1. Therefore, the sine of 1 over x is also bounded by -1 and +1. What we need is x times sine 1 over x. So this one. To get that, notice that if x is positive, then multiplying x to each functions Each of these expressions will result to that one. And when x is negative, then it results to direction of inequalities reversed. So how do we get around this? Or what I mean is, how do we find the two sandwiching function that sandwiches the g of x no matter the sign of x? Because we need the values of x from the left and from the right of 0. So what we do is we take the absolute value. So we are sure that no matter what the sign of x is, the absolute value, the negative of the absolute value of x and the positive of the absolute value of x sandwich the x, sine 1 over x. So again, the function g of x is now sandwiched. The next thing to do is to identify the limits of these two sandwiching functions. So the limit of the below function is 0. The limit of the above function is also 0. And therefore, the limit of the function being sandwiched is also 0. Summary of techniques. When tackling limit problems, remember these key strategies. First, the first move is to always try direct substitution. If it fails, meaning you get 0 in the denominator, then either the limit does not exist or it is in the indeterminate form. In the case of the latter, the indeterminate form or 0 over 0, the following techniques might be able to help. So, if a rational function yields 0 over 0 after direct substitution, chances are this function has common factors in the numerator and the denominator that cause such a result. In that case, cancellation can be used to find the limit. Second, some rational functions that have common factors in the numerator and in the denominator but are concealed by radicals. In this case, we first need to do the process called rationalizing technique that involves conjugates, multiplying by conjugates, and simplifying. And in so doing, the hidden factors will come out, making cancellation technique possible again. The third one is rational functions that can neither be solved by cancellation nor rationalizing techniques such as sine x over x. Hence, a more advanced technique is needed. The property called the Squeeze Theorem responds to that call. This theorem yields two special limits, those two. The challenge in this technique, again, is to find two functions with the same limit at the given point and sandwich the f of x. But with sufficient practice, you will be able to develop a mathematical instinct that can help you identify such functions. So I guess you are now ready to apply these new techniques that you learned in this lecture.